guys, Mrs. Banky here. I have the sniffles. I'll try that again. Hi guys, Mrs. Banky here. Today I'm making a video that will show how to practice using the periodic table to get electron configuration and review a couple of the exceptions. This is particularly aimed at students who were absent on the day that I went through this series of questions. We did some review in class. We worked on the whiteboards, and one thing that you have to have handy is your periodic table from the beginning of the year, in which you have your groups labeled, like Group 1 is the alkali metals, Group 2 is the alkaline earth elements. We have our transition elements here, and another main group is our halogens, which is here, and our noble gases. So these are not labeled on this particular periodic table. So looking at how to use the periodic table to get electron configuration for the group 14 element in period 4, I look for group 14. The brown on here is group number, and in period 4 is going to be this element right here. So a way to use the periodic table is to start at the beginning and just make your way through the blocks until you get to the element you're at. So here is 1s2, so I'm just going to write 1s2. Next, 2s2, still not there. 2p6. 3s2, still not there. 3p6. 4s2. If you labeled your periodic table correctly, you should have that 3D there, so 3d10. I went through that entire block from beginning to end without getting to my element, so I'll add that. 3d10. And then 4p1, 4p2. So we're in the fourth period, and we are at p2. So 4p2 is, this is the full configuration for germanium. Another thing that we talked about in class is how to do a noble gas configuration, or a noble gas notation. To do that, you identify the element that you're interested in, and then you bump up a row and look at the noble gas that's in the row right above it. In this case, it happens to be argon. So the configuration for argon is everything up through 3p6. See, argon will end in 3p6. So a shorthand way to write electron configuration is the noble gas configuration. So what I'm going to do is I'm going to put argon in a bracket, and then from argon, beyond argon, what do we have? We have a 4s2, 3d10, 4p2. So this is the noble gas notation, or noble gas configuration for argon. I am not crying. My eyes are watering from allergies, and I have the sniffles, and I ask that you please bear with me, please, because there's nothing I can do about it, and I have to get this video made. So let's go on to the next thing. Oh, no, we're not going on to the next thing, because what I asked students in class is if they were building this model for argon, how many energy levels the model would have, how many electron shells the model would have. And everybody looked at it and agreed that we would have 4 energy shells. So we would have electrons in the first, in the second, in the third, and in the fourth. And if you look at this configuration, you can ask yourself, how many valence electrons are there? And to do that, you look at the uppermost energy level, which is the fourth. And in the fourth energy level, we have 2 electrons here, plus another 2. So we have a total of 4 valence electrons. I reminded students that another way that you can easily get the number of valence electrons when you're using the periodic table is to simply look at the group numbers. Now, this does not work for the transition elements, but it does work for the main group elements, which include the S and the P block. So group 1 has 1 valence electron, group 2 has 2 valence electrons. And if we look at the last number in each of these numbers, it tells us the numbers of valence electrons. All of the elements in group 13 have 3 valence electrons, 14 have 4 valence electrons, 18 has 8 valence electrons, with the exception of helium, which has 2. Now, we will move on to the next thing. And, I just have to push the arrow. There we go. Here it says, write the noble gas notation for the only metal in group 15. Okay, so you need to rely on your periodic table. And when we look at our periodic table, there is this ziggity-zaggity line, and I'm just looking up at the wall to make sure that I put this in there. It goes between aluminum and silicon, and then like this, arsenic, and then down like this, tellurium, and actinium. And these elements are called the metalloids. So, and boron is also considered a metalloid. So all of the elements on this side are nonmetals. All of the elements on this side are metals. And I forgot that antimony, Sb, is a nonmetal, or a metalloid, sorry. So the only metal in group 15 happens to be bismuth. Now, one thing that this periodic table is missing in its labels is the fact that between here and here, we have the 4F and the 5F elements. And I'm just going to put this bold here as a reminder that once we get to this, and I do realize that the gap here is between 57 and 72. Some periodic tables do have it differently, but we're going to use this as our boundary. So from 6S, we would encounter 4F. I'm sorry, so, whoops, we would go from 6S, hitting this boundary, 4F, alright, that would be the entire 4F row, this is a 5D, it's kind of hard to see on there, 5D, and then on the other side of the 5D is up to the 6P. So the order of filling goes from the 6S to the 4F to the 5D to the 6P. So we'll do a long electron configuration for the only metal, which is bismuth. And actually, I won't do a long, I asked students to do a long one in class, but I'm not going to right now. We'll do a noble configuration. So with the noble configuration, looking up at the line above it, what noble gas is there? It happens to be xenon. So I put xenon in brackets, and then everything beyond xenon is what the configuration is going to be. So that gives us 6s2. Oh, there's the boundary down to the 4f. And it would include all of the 4f's, F14. Now we're back up to 5d. And we have 5d10. And then 6p1, p2, p3, 6p3. Now, if you asked students, if I asked you to how many energy levels there would be if we were building this particular element, bismuth, there would be 6, because we have electrons occupying the 6th energy level. How many, I may ask? It is 5. But guess what? We didn't have to look at the configuration to do that, right? Because bismuth is right here in group 15. So there are 5 valence electrons. Alrighty, let's try the next thing. Write the noble gas notation for the transition metal with the smallest atomic mass. Okay, the D block are my transition elements or transition metals. Which one is going to have the smallest mass? Well, this one has the smallest atomic number, and I cannot see from here. Oh, there's a periodic table right in front of me. Excuse me. It's a good thing I have these glasses on because I can see it actually. The mass of scandium is 44.96. The one right next to it is definitely more massive, 47.87. So scandium is the element that is a transition metal with the smallest atomic mass. Alright, starting from the top, doing a full configuration. I have a 1s2. To the next one, 2s2. 2p6. Ooh, that was kind of messy. I'm not going to go back now. 3s2. 3p6. And 4s2. Boom. 3d1. Just like that. And let's practice again with the noble configuration. Scandium, looking up to the row above it. The noble gas is argon. Putting that in a bracket. And everything beyond that is a 4s2, 3d1. And we have the noble configuration for scandium. Pretty slick. You may be wondering why I didn't use the periodic table to teach you how to do electron configurations in the past. Well, I don't think that I would have been able to do the Hogg-Hilton activity in which we had little piggies in rooms facing each other and not facing each other. Oh, I broke the rule. This would never happen. Because if this was a p sublevel, an electron would go into, not an electron, a little piggy, would go into each of the hotel rooms before they get doubled up. So, I wanted you to get a sense of where these numbers actually came from. But you can see that very quickly. You can get an electron configuration using the periodic table. For example, I will get the configuration for titanium. I can very quickly 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d5. So very quickly. And the noble configuration, even faster. Krypton in a bracket, 5s2, 4d5. So very quickly this can be done. Alright, let's see what the next slide says. It says, write the noble gas notation for the alkaline earth metal with the largest atomic mass. If you look at your periodic table that we did at the beginning of the year, you know that this group right here is the alkaline earth elements, or alkaline earth metals. The one with the largest mass is radium. It is called radium. I just wanted to make sure that it wasn't radon. Alright, so radium. Now all I'm asking for is the noble gas notation, and look at this. It's going to be the shortest one of them all, and it's one of the biggest elements on here. So all I need to do is boom, up to the noble gas on the line right before it, Rn, which is radon, 7s2. Done. Just like that. Okay. There are a couple things that I want to go through in this video, and that is not that. And that are that I can't even talk. That includes some exceptions to the octet rule. So, exceptions. Oh, I'm just making stuff up right now. I'm talking about the octet rule, which isn't even the topic that we're talking about. And that's something for the future, and I'm really sorry. I totally messed that up. But I don't have time to edit it out of here, so you can just bear with me in my messiness. So these are exceptions to electron configuration. And one is for the element chromium. Now I'm just going to do an orbital notation for chromium. 1s, 2s, 2p, 3s, 3p, 4s, and 3d. So we have this sublevel here with 5 rooms, sublevel here with 3 rooms, and also this P has 3 rooms. So chromium, when I start putting my electrons on in the way that we already have, or always have, 1, 2, there are 24 electrons, 3, 4, 5, 6, 7, 8, 9, 10. Each orbital will have 1 electron before a second is added. Notice I'm putting them in there with the opposite spin. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, well, they have discovered that. And if you look, chromium here is in the D4. It would end in 3D4. They have actually discovered that chromium only has 1 s electron. That this s electron is actually in that 5th orbital at that 3D sublevel. And they figure that this element is more stable, having this orbital half filled instead of having only 4 there. So the configuration for chromium is indeed, I will do a noble configuration. So above chromium I have argon, 4s2. I'm sorry, it is not 4s2. It is 4s1. That's what makes this unique. 4s1, 3d5. So there are actually 2 elements that end in 3d5, both chromium and manganese. Okay, copper is very similar. I'll just put the s orbitals up here. So s, and then we have our 3d. If we did the configuration it would have, oh, that's really messy. It would have a total of 9 electrons in that D sublevel. And copper is the same. One of these electrons does go into that D sublevel. So copper is another element that only has one s electron. So copper is also a 4s1, 3d, 10. My pen started writing like a kindergartner again. So there are 2 elements that end in 3d10. So these are the 2 exceptions that you're responsible for. So I tricked students in class and I told them to write the configuration for element number 24 or 29. It was either chromium or copper. And I had these exceptions written on the board at the time. And some students figured out what I was doing, that I was trying to trick them. But many did this configuration with a 4s2 3d4. And I had to tell them they were wrong. And that's kind of heartbreaking to some who felt like they were doing so good. But then I revealed that it's just an exception and they actually were using the right process. So then they felt better about themselves and the whole world was a happy place. Alright, the last thing that we talked about during this lesson was students answered these questions. Give the symbol, group, let me get my pen again. Give this, why is it red? Oh, geez Louise, bear with my messiness again, please. I don't know how it turned red. I don't want it to be red. I want it to be blue. Alright. So, we need the symbol, the period, and periods go like this on the periodic table, and our options are 1 through 7. The group and the block. It is going to be either group 1 through 18 and block S, P, D, or F. So you can pause it right now and practice if you like. One thing that I did do, because it was really hard for kids to see, is I wrote these a little bit bigger. And the resource that I got this from actually puts the configuration in numerical order. And I would typically not write this configuration like that. I would write it like this in the order that electrons fill. So 4s1, 3d5. Okay, so for the first we have sulfur. The symbol is S. I don't have this memorized, so I will model looking at my periodic table. Sulfur is in period 3. It's in group 16, and it is in the P block. Nickel, the symbol is Ni. Nickel is in period 4, group number 10, and it is in the D block. This element right here, there's only one element that will end in a 5s1, and that is rubidium, Rb. It is in the 5th period, in the first group, group 1, and it is an S block element. And this element, tricky, has only one 4s electron, and it has 5 3d electrons. So remember, that's one of the exceptions to electron configuration, not the octet rule. Chromium, it is in period 4. It is in group 6, and it is in the D block. And this is where our lesson ended. We did practice with some others on the whiteboard, but we will be having a quiz on this, so I wanted to prepare you. Now, the date of this is March 21st, 2017. So, if you're watching this in the future, this may not pertain to you. But on this day, the next class meeting that we have, my students will be having a quiz, and they will have to answer questions like this. So that's all I have. Thank you very much. That is the end of my slide presentation.